Hello again, it's Ray DeLucci. This is actually this talk on does molecular hydrogen equal dark matter. Will follow a bit from what Bob talked about this morning in the infamous galactic rotation curves. Well, no, I won't necessarily explain the curves. They'll look into whether or not molecular hydrogen is a plausible explanation for what constitutes dark matter. And again, I'll be looking at other people's theories. We'll start with another stylized version of the curve that you saw this morning. We have the expected Keplerian velocities, tangential velocities of the stars as you go out farther and farther along the galactic disk. You have what would be constant velocity here shown in red, the velocity of a solid body, which would just, again, the angular velocity would be constant, so the tangential velocity would just go proportional with r. And then we have what's observed, which is an initially rising tangential velocity that matches that of a solid body, and then the flattening that matches that of a constant, which doesn't really follow either a pinwheel or any of the standard ones. So it's definitely an anomaly. Dark matter was first postulated by Jan Oort of the famous Oort cloud in 1932 to account for the orbital velocities of stars in the Milky Way, and by Fritz Zwicky in 1933 to account for evidence of missing mass in the orbital velocities of galaxies and clusters. However, the first person to postulate dark matter was based upon robust evidence was from Vera Rubin's studies in the 60s and 70s, where she actually measured a lot of these galactic rotation curves. And again, this is a stylized one, but there's a lot of them, not just the Milky Way, and while they're not all flattening out, some do decrease, some do increase. In general, this is kind of the shape that you're going to see with most of the galactic rotation curves. Most stars and spiral galaxies orbit at roughly the same speed, which implied that the mass densities of the galaxies were uniform well beyond the regions containing most of the stars, if you only accept gravity as an explanation. And as Bob showed earlier, you play with the equation for galactic effect and the rotation curve. You can't change the G, you can't change the R, so you play games with the M. Eventually, other astronomers began to corroborate her work, and it soon became well established that most galaxies were dominated by dark matter. And by the 80s, most astrophysicists accepted its existence, and of course it's sacred today, and if you want lots of research money, you go out and search for dark matter and find something, and something is found every year, and Nobel Prizes and all that good stuff. Does molecular hydrogen constitute dark matter? 1966, Varsavsky observed that the appearance of the rotation curve of the Milky Way galaxy implies that molecular hydrogen could have an abundance comparable or actually higher by a factor of about 4 to that of atomic hydrogen. If a large fraction of the unseen mass is gas distributed near the plane of the galaxy, and this gas can be molecular hydrogen, we could postulate an abundance up to 5 times larger than atomic hydrogen and still satisfy all the observations of the motions of the stars. And he published this in Space Science Reviews back in '66. So this was the first mention of molecular hydrogen being a potential candidate for dark matter. In '89, Paul Marmé and Ribert commented that the largest fraction of gases in space cannot be atomic hydrogen, but possibly can be molecular hydrogen, which is undetectable in 21 centimeter radio receivers. And that's the wavelength at which atomic hydrogen absorbs and emits radiation. That was published in the IEEE transactions. 6 years later, Marmé offered the emission of the 3-degree Kelvin Planck radiation isotropically in all directions from molecular hydrogen as an alternative to the Big Bang to explain the cosmic microwave background, CMB. He said that astronomical observations show that there is a very large quantity of atomic hydrogen in the universe, which is quite unstable. These atoms react between themselves to form molecular hydrogen, which is extremely stable, down to the most extreme vacuum. After billions of years, an important fraction of atomic hydrogen in the universe is already combined to form molecular hydrogen, among the most transparent gases in the universe. Consequently, one cannot hope to detect free hydrogen in space or free molecular hydrogen in space by the usual spectroscopic means. And that was published in the Period. Molecular hydrogen has been a leading candidate for dark matter, at least within a galaxy, for 50 years or more, not to mention Marmay's conjecture that it could be an explanation for the cosmic microwave background, again, going back to Varsavsky in '66. At least traces of it have been identified in our galaxy and other galaxies, remarkable given its extreme difficulty to detect. If molecular hydrogen is indeed the majority of the alleged dark matter that permeates throughout our Milky Way galaxy and causes its anomalous rotation, an analysis of its gravitational effects might lend some evidence to the validity of this postulate. And just to mention, mainstream doesn't necessarily favor, molecular hydrogen is too normal a type of matter, and typically when they're looking for dark matter, they're always looking for something more exotic than boring old molecular hydrogen. So the people who propose this still fall into the dissonant ranks because molecular hydrogen is not the type of dark matter that the mainstream is interested in, and certainly probably wouldn't give you a Nobel Prize for detecting it. For gravity and the galactic rotation, the Milky Way will model it as a circular disk of uniform density due to the presence of molecular hydrogen as dark matter, permeating the entire disk. We'll put the core at the center and a star of sun mass m at a radius r. For a solid sphere of uniform density, gravity linearly increases linearly with r from 0 at the center to maximum at the surface. Mass is proportional to r cubed, the distance to r squared, the ratio is proportional to r, and it's arising solely from the spherical mass that's less than r, within the range of the galaxy itself. So that's for the solid sphere. An analogy for the disk, the mass is proportional to r squared, the distance is proportional to r squared, so we would expect it to be constant. So throughout the galactic disk, the gravity from the disk at any r is constant, gm, mass of the galaxy, m, mass of the star, over r squared, radius of the galaxy, for galactic mass m, galactus radius capital R, and star mass m. Here's a couple of plots using those formulae, including the gravitational force from the galactic core, written as g, the gravitational constant, mu, which is the mass of the core, m, which is the mass of the star, and r squared, where r is the radius of the core, or the distance from the core to the star. The total gravitational force on the star as a function of r is just the sum of the core plus the sum of the disk contribution. From this, equating the total gravitational force to the centripetal force at r, and centripetal force will be part of the trial tomorrow, we obtain the force total at radius r is m, velocity at radius r squared over r, which implies that the velocity at radius r is equal to the square root of the radius, the force at radius r divided by the mass of the star, where v sub r is the tangential speed at r, not the angular speed. And so if we scale gravity to 1 being the maximum over there, we see that the total from the disk is essentially constant, while that from the core drops off, as the formulas show. So what does this imply for the tangential speed, which is used for the galaxy rotation curves? The tangential speed continues to rise out to the edge of the galaxy. So you see, this is what this would imply if molecular hydrogen was uniformly distributed. You'd have a v proportional to the square root of r, despite the fact that the gravitational force is essentially constant throughout. Again, as you can see here, given the scale, the core is contributing less than 1% very quickly compared to the contribution from the disk. So as you go farther and farther out, it's the disk that's dominating. However, after a quick initial drop, the angular speed, shown here in red, omega r equals the tangential speed at r over r, levels off, declining gradually with distance. So we don't see a flattening of the tangential speed as implied by the galactic rotation curves, but we do see a flattening of the angular speed because it's essentially proportional to 1 over the square root of r, and that's fairly insensitive to r as the radial distance from the galactic center increases. The tangential speed across the galactic disk, if anything, approaches that of a solid body, exhibiting dependence with the square root of r rather than r itself. And again, if we go back earlier to the idealized curve, the solid body, pinwheel type of galaxy rotation is this straight green line. And what we see with the galactic rotation based on the tangential speed, oops, too far. We see this, while it's not a straight line, it's the only curve that shows the increase with distance. This is reinforced by the tendency for the angular speed to level off with radial distance, although still showing some gradual decrease. So what we're seeing, if the tangential speed or the angular speed flattens out, that's implying a solid body type rotation or the pinwheel rotation for a galaxy. And they are not alleged to rotate as pinwheels for the most part. And I have another paper. The whole galactic rotation curve issue confuses me, because if the tangential speed is constant, the spiral arms should be unwinding. Because in order for the spiral arms not to unwind, you need the angular speed to be the thing that's constant as you go out, not the tangential speed. So when they say there's a galactic rotation anomaly, and they show a flattening tangential speed, and then they claim the galactic arms don't unwind because the rotation speed stays constant, it doesn't make sense. And the mainstream explanation, which I won't go into here, is what is it? Gravity? It's waves. It's some sort of resonance waves that are going on, and there's problems with that as well, which again is another paper. It appears that from this highly simplified analysis, assuming uniformly distributed dark matter throughout the galactic disk falls somewhat short of explaining the galactic rotation anomaly by itself. So even if we wanted molecular hydrogen to be the candidate for dark matter, if it was uniformly distributed, or any type of dark matter was uniformly distributed, we would not be seeing the galactic rotation curves that are being detected. Are there other explanations? Electromagnetic phenomena have been proposed as mechanisms that account for the flattening of the galactic tangential rotation curve, including ones that exclusively invoke electric or plasma universe theory, and even one of the author's own. And I presented this last year as I gave my own theory, which is rare because I usually don't come up with theories, to try and explain the galactic rotation curve based on electromagnetic theory. A recent one is of particular interest is that of Donald Scott, and if you're a fan of the electric universe, he's one of the big names there, and there's a lot of the theoretical studies. He's come up with the Birkeland current Bessel function model. It's been published in Progress in Physics. It's also online. He has a nice presentation that I watched and extracted quotes from. And this is his model here. He compares predicted and actual stellar velocity profiles. And what he has come up with is velocity proportional to the square root of r. We're back here. Velocity proportional to the square root of r. So you can see that while this fits part of the curve, maybe out to about halfway out through the galaxy, it doesn't flatten as the galactic rotation curves do. So it doesn't completely cover the entire galactic rotation curve, but it covers a large portion of this idealized. It doesn't get into the blips here that Bob was trying to explain with the differences between the spiral arms and then the empty areas in between there. And this is a quote from Scott's presentation on the Electric Universe website. If you take my model of the Birkeland current and assume that it's feeding the rotation in the Birkeland current and is responsible for the rotation of the galaxy, that is the comparison between the actual velocity, which is that sort of wiggly, sort of very lazy S curve, and the square root of r as the smoother curve, that's exactly what my Birkeland current model predicts should happen. What he doesn't add here is that only counts out to about halfway, because he has 40 distance units here, and it fits pretty well out to 20 and starts deviating a little bit past there. Still, it's a very interesting model. Another interesting proposal in a paper that I found, Paul Marmay's son Louis, another that while providing a strict gravitational explanation still leaves room for the possibility of electromagnetic effects, is that from Louis Marmay. And he's published this in Archive, which is, he's managed to get himself into a mainstream publication. I've tried that and I can't get a sponsor even though I tried 100 different people. So they're closed, and that's why there's FIXRO, which is Archive spelled backwards. They'll publish anything you want to put in there. Given the rotation curve, the intrinsic angular momentum, the maximum radius, and the smooth mass distributions as boundary conditions, the unique mass distribution is obtained, which is finite and does not have to fit a simple analytical function. The additional mass is provided by baryonic matter that most likely to be molecular hydrogen and condensed matter. Also, calculations with plasmas also produce mass based on his double mass distribution of molecular hydrogen and not as much explain galaxy dynamics. It would be important to know which fraction of interstellar matter is plasma and contributes as such. So he's opened the door to both the gravitational and electromagnetic explanation for the galactic rotation, room for a plasma as well. And he's got some good derivations within galaxies. At least my simple analysis suggests that it alone may not be sufficient to explain the anomalous Archive site. In conclusion, while molecular hydrogen appears as a plausible candidate, distributed uniformly throughout the galaxy of a disk, dark matter does not produce the observed flattening, but suggests rotational behavior approaching that of a solid body or pinwheel, which is also suggested by the angular speed variation. This behavior is also suggested by Scott's Birkeland current Bessel function model, that is, tangential speed varying with the square root of radius, but not the radius itself, which would be consistent with a solid body rotation. Another alternative was proposed by Louis Marmay and assumes a double mass distribution of molecular hydrogen as the dark matter within a galactic disk, although it does not dismiss the possibility of electromagnetic effects as well. And my question, by combining gravitational and electromagnetic phenomena, each sufficient alone only to cause tangential speed to vary with the square root of radius, lead to the solid body rotational behavior where the speed varies directly with the radius. And that concludes the first talk.
Okay, questions on this? Again, please state your name. Let's also, one of the things I'd like to do is let's try to talk and the same thing. I think that would just make it a little easier for everybody. Okay, go ahead. First question, please. To talk, I know everybody has their own ideas and explaining about that, but that's why we have the other sessions. So let's keep the questions and comments about the particular topic and keep off our own.
Milgram has examined the 900 spiral galaxies, the data for that, and found that it is explained by modified Newtonian dynamics. And not only does it explain the spiral galaxies, velocities of the outer arms, but it also explains the galactic luminosity, and it explains the optical rotation curves of the galaxies. This is the only complete explanation in the literature, and you might want to look at that. It's just requires one additional term in addition to Newtonian dynamics, and it doesn't require any dark matter or anything like that.
I've also found in the paper I presented last year, I found at least 3 other explanations for the rotation anomaly, one of which deals strictly with the tapering shape of the spiral arms, and a very complex simulation that was done by Carl Johnson, and a very interesting model there. Ken Hughes has a model where he invokes relativity and time dilation, length contraction, and the relative position of us in our own galaxy, and the outer parts going faster than the inner parts slower, and how the speed is perceived as an explanation. And the third, of course, is the electromagnetic phenomena, where it's basically it's the Faraday motor type of explanation. So in the paper last year, I showed also 3 other ones in addition to the one you cite.
They don't fit the data to 99% accuracy.
Well, that I don't know.
900 galaxies.
I don't know
really
if they
good.
did that or not. But
And
I know there's a lot of speculation
They
out
do
there.
the luminosity curves also, which the other theories don't do. So it's the big picture you have to look at, I think.
Duncan Shaw, is this coming through?
Yeah, just
Thank you.
Thank you. Duncan, put it like this, vertical. Thank you.
I got it? All right. Thank you for what you've had to say. The one question that comes to my mind is, what causes the rotation in the first place? And is there any paper that you are aware of which suggests that it comes back to fundamental particles or cells of an ether type, which are asymmetric, so that when they bump into each other, there's always a turning result from the bumping into each other, which could have an overall turning effect. Are you aware of any paper of that nature? I'm not, but it's
the one study I've seen that tries to, I mean, of course, the mainstream explanation is as matter starts compressing. It's the same for solar systems. Matter starts compressing, and it gets in, and it starts spinning, and the spin is inherent. The one simulation I've seen for the initial formation of the spiral. Okay. Here we're going to deal with galactic recessional speed. So we're back to expanding universe type stuff, not galactic rotation. So as you can see, my 4 papers this year, I focused on my galaxy studies. And so this one is, does galactic recessional speed increase with distance? Redshift, does redshift imply an expanding universe? This is a typical expanding universe linear curve, which you can see there's a big blob over here that, you know, kind of the regression analysis is dominated by the rest of the curve. This part here doesn't really support anything. But we have Hubble's law, which is V equals the Hubble constant times the distance from the observer. It's typically based on fitting data for relatively low, on a universal scale, redshifts and distances. At larger redshifts and distances, approaching the reputed size of the observable universe, which is 14 billion light years, a simple recession velocity, v, is given by multiplying the co-moving distance, d, of the object by the Hubble parameter at the redshift h as z equals hd over v minus 1. So it's not just hd, it's a bit of a, there's another term in here, and this is from a mainstream astronomy site. Hubble's law is based on the lower range of galactic redshifts and distances, and extrapolated to the higher redshifts and distances to support the theory of universal expansion. My goal was to revisit this over the full range of redshifts and distances as tabulated by John Gowan in his study, A Space Map of the Universe, Implications for Cosmology and Inflation. And that's his website if you're interested in his work. He compiled a chart of redshift versus distance, and these are the distances, and these are his measured redshifts. He had 27 redshifts versus distance, redshifts from 0.04 to at 4 times 10 to the 8th light years, all the way out to 18.3 at 13.4 times 10 to the 10th light years from Earth. So I just did a best fit to Gowan's data. I just used an online nonlinear regression fitting curve, and I tried a polynomial formula fell out, and a logarithmic formula fell out. And as you can see, this graph here, which has Gowan's data, the logarithmic fit, and the polynomial fit are all quite good. So since both of these fits are quite good, I just told, for proceeding, for my analysis, I took the simpler one, which has less terms in it, which is the logarithmic one. the results would apply with polynomial as well. So with recession speed versus distance, using the logarithmic formula, I project the recession speeds, which are scaled to the Hubble constant h, as a function of distance for both the linear Hubble law, v over h equals d, and the nonlinear approximation, the more exact one, which is v equals h over hd over 1 plus the redshift as a function of d. And we have the speed here relative to the Hubble constant, and here we have the distances. Here we have the Hubble, the simpler Hubble fit, and here we have the fit where we use this equation, but where I use my formula for z of d from the logarithmic curve. For the calculation, I use an average value for the Hubble constant of 70 kilometers per second megaparsec. The recession, we can see here that the recession speeds approach that of light based on the Hubble law, and they go out as high here when we're getting out to a little over 13 billion light years away. You can see the ratio v over h is a little over 4,000, and if you multiply that by the Hubble constant, we're getting out to 0.96 c as the recession speed out at the edges of the alleged edges of the observable universe. But if we look at the nonlinear approximation based on Gowin's data, we see that it actually has a much lower peak and actually stops dropping off with distance. This peak occurs here at around 9 billion light years, approaches a ratio of 1,500 for the speed over the Hubble constant, and converts into about 1/3 the speed of light. So a factor of 3 difference for the maxima between the standard Hubble law and the more detailed Hubble law with the substitution of the redshift derived from Gowin's data from my logarithmic analysis. The peak occurs for the nonlinear approximation around the distance of 9 billion light years from Earth. The redshift calculated there is about 1. And these are the actual values here that for the two curves, this table. There is a distinct deviation from linear behavior for the latter as low as about 3 billion light years from Earth. And you can see here that this curve starts flattening out around 3 billion light years away. It peaks at about 9 billion light years away and then drops down as you go out farther. At this point here, at 3 billion light years, the redshift's about 0.25. There's a decrease that goes from 9 billion out onward, and when you're getting out here, you have very high redshifts, greater than 1. Gowin had one as high as 18.3. What might this indicate? My speculations. How to explain the anomalous behavior of recession speed when it's scaled to the Hubble constant, resulting from the nonlinear approximation, which was based on Gowin's data. The 3 best and simplest regression fits up to a distance now of only 9 billion light years. So now I'm looking only at fitting curves out to this point as opposed to fitting the entire curve. I ended up using the same regression software online, a sinusoidal, an inverse, and a logarithmic fit for the v over h ratio. The 3 of them are shown here. So I'm going to assume a reference point to be located at a distance which is 9 billion light years from Earth, which corresponds to the maximum ratio for each of these. Again, our maximum occurred here at 9 billion light years, and I'm going to look at the behavior just out to 9 billion light years. I'm not going to look at this part of the curve for now. As one proceeds away from this reference point, 9 billion light years away, so here I'm going to be moving leftward on the plot, the v over h ratio decreases. You can see v over h drops down. And that's the same whether I use the sinusoidal, the inverse, or the logarithmic fit, or the actual data itself from Gowin. For convenience, these ratios as scaled to a maximum value, they're scaled and plotted against the distance from Earth. All 3 fits are quite close to the actual ratios. From these fits, what phenomena might generate the anomalous behavior in the recession speed? If the effect was gravitational based on some sort of great attractor or great wall, and these are alleged to be structures in the universe where galaxies are clustered together, and it's not isotropic. Even when you look at the cosmic microwave background map that they show, there's clumps here or there, which of course pose a problem for mainstream who thinks everything should be uniform, so you got inflation and stuff like that to explain that away. This is perhaps analogous to these. There are reputed to be great attractors or great walls located about 300 million and 400 to 500 million light years away from Earth. And you can find that on Wikipedia. An inverse distance squared behavior might be expected. So we would think if the recession speeds were gravitationally dominated by these dominant masses out at certain distances, as you moved away from these locations, you'd expect to see some sort of 1/r² behavior. We don't see this as a result of the data here. We've got some sort of very smoothly decreasing function as we move away from the 9 billion light year maximum. Is electromagnetism a possible explanation? The electric and plasma universe has a hypothesis for this. They cite Ampere's law for a long conductor with current I indicates an inverse distance radius behavior for the generated magnetic field. That's the formula there. If at a distance 9 billion light years from Earth there were another great attractor or great wall in the form of a long electromagnetic plasma filament consisting perhaps of many galaxies, such a magnetic field decreasing inversely with distance from the filament might be generated. So you look back here, and while this is not a linear decrease, it's closer to a linear decrease than any type of 1/r². It would pull on nearby galaxies, resulting in attractive speeds that decrease with distance. Combined with relative motion away from this filament by the Earth moving itself, and either the filament or the Earth, or both could be moving, perhaps analogous to the constant term in the inverse fit. And again, when I was doing my fits here, looking at the inverse fit, I have a constant here in the denominator that goes along with the d. So it's not strictly inverse to distance, it's inverse plus a constant term. So combined with the relative motion away from this filament by the Earth, perhaps analogous to the constant term I just showed, might this type of behavior result? That's my question. Roger Ryden, who used to present at the NPA conferences, and I remember going to the one, I think it was 2011, maybe, he presented his big wave theory, and this is his wave site, and his analysis. All the mass and gravitons in the central black hole, if you believe in black holes, dissociate simultaneously and proceed together outward from the origin at the speed of light as a correlated symmetric spherical wave. New matter is created along the radial direction as the wave recedes from the origin. A series of deep redshift galaxy count measurements exhibit the same periodic behavior, but with some distortion in the 45-degree traverse, indicating that the data are sampling a spherical distribution centered near the Milky Way. So results of his analysis showed that if there was a Big Bang-like explosion, it wasn't too far away from us. He postulates a spherical Bessel function squared solution times an exponential that accounts for matter deposition losses, and he finds that it measures the deep redshift north to south galactic pencil surveys when scaled by the inverse of the square of the radial distance. So he developed what he calls the new big wave model and predicts that periodic correlated great walls and voids will form in the universe and places the origin of the initial Big Bang somewhere to the side of the Milky Way. And it's, again, the 2011 NPA proceedings has this in there and his website. So he's seeing a series of great walls, and that's not inconsistent with a possible explanation for this anomaly in the galactic recession speed based on the Gowan data. Let's relax Ryden's assumption that there was a Big Bang, likely in the relative near vicinity of the Milky Way, which in his model was only 70 million light years away from us, to be merely that a Big Bang-like explosion, that is, an event that may repeatedly occur at different locations within the universe, happened approximately 9 billion years ago. So let's say there are big bangs, but they don't create the universe. They occur sporadically in the universe. It traveled spherically outward at approximately light speed, such that the density of matter varies sinusoidally, which is the form of the J0 Bessel function, with distance away from the peak density, which now happens to be located 9 billion light years away. The effect of this sinusoidally increasing density, proceeding away from Earth, can be gravitational and or electromagnetic, such that galactic recessional speeds reflected by the sinusoidal model might be observed from Earth. So if we take the sinusoidal V over H ratio at set distances of 9, 7.2, 5.4, 3.6, and 1.8 billion light years away, and we look at that against the J0 Bessel function at the Bessel parameters here, we see that, and after I scale them, we see only slightly higher values, deviating at most by 50% here. The J0 Bessel function symmetry about the y-axis suggests some parallel to the decreasing recessional speeds with distance from Earth beyond 9 billion light years. So this is highly speculative, but is it at least possible that the observed behavior of galactic recessional speeds could be related to Ryden's big wave theory? So putting the math to Ryden's theory and the sinusoidal fit that came from looking at Gowan's data, it makes his explanation plausible. In conclusion, analysis of redshift versus distance data for galaxies over the full range of observable universe suggests an anomalous increase, then decrease of galactic recessional speed, peaking around 9 billion light years from Earth. My speculations is that some electromagnetic phenomena somehow connected to electric or plasma universe hypotheses. Was there an ancient Big Bang-like explosion relatively near the Milky Way, as postulated by Ryden, and a very liberal extension of his big wave theory? The analysis casts doubt on cosmic expansion due to a universe birthing Big Bang and the recent additions of dark matter and energy to counteract holes in the standard model. But I'm offering it only as food for thought as to what truly might be occurring and the actual interpretation of the reputed cosmological redshifts versus distance. I'd just like to acknowledge that John Gowan did review my paper. He offered some insights. He gave me some feedback and was kind enough to respond and offer some possible explanations. While I'm not a proponent of the Big Bang, cosmic expansion, etc., I can't justifiably comment on the insights except to accept Gowan's redshift versus distance data as accurate. He does believe in the Big Bang and cosmic expansion, so he's mainstream in that sense. But I concur with his rejection of some mysterious dark energy, but remain skeptical regarding any sort of gravitational explanation for the anomaly. Given that it's difficult to relate it to some sort of inverse squared, distance squared behavior, as I showed earlier, we don't see that inverse squared behavior. And that concludes my last paper.
Okay, questions? Remember to give your name first and turn on the mic.
I'm Cameron Repixel. It seems that you are believing the universe is expanding some sort, right?
No, I don't believe it's expanding. I'm saying the theories that I examined here are looking for alternate explanations to an expanding universe. And the electromagnetic theory was one. Gowan's, the assumption is that distance is measured by redshift. So the higher the redshift, the farther the distance. We don't really know how far anything is that's out there, because once you're out beyond a certain distance, you can't use parallax anymore. So they say, well, there's standard candles for some of the stars and some of the galaxies. Well, that only works out to, again, a certain distance. And then there's the type 1 or type 1a supernova. The assumption is they're always the same. So whenever we observe one out there, we look at the broadening of the light spectrum. That proves that there's no tired light. So everything that's used to measure distance of galaxies is based on assumptions. And so what Gowan just basically what he did is he said, I don't see this linear Hubble-like cosmic expansion behavior at large redshifts measured at great distances, and that's what his data showed. So I'm not advocating an expanding universe here.
The problem is, if the universe is not expanding, it will be static.
Yeah.
Yeah, we have only two choices.
Most likely, yeah. And that's I'm more of a proponent of a static. In my paper earlier today, I showed the arguments to, the galactic density was more favorable towards a static than an expanding universe. So as far as my personal beliefs, I believe more in a steady state type universe, I think the redshifts are due to a tired light type of, some sort of tired light phenomenon myself,
Okay,
which I've talked about at other conferences.
When it is, if this is static, what sustains the universe to a certain size so that it can resist the implosive gravitation force?
Again, I don't have a speculation that, again, if there's electromagnetism, if electromagnetism pervades the entire universe, if you're a plasma universe fan, the magnetic fields may just hold it where it is. I mean, one explanation for the galactic rotation phenomena, and it's not I didn't show it here, but in last year's paper, the magnetic fields follow the spiral arms. So if you've got this pseudo-frozen magnetic field across a galaxy, your galaxy is going to spin like a pinwheel because electromagnetic forces are going to dominate over gravity. So if the universe, if it's static, of approaching infinite size, it may move around locally, but in general, there's no compulsion for it to go farther apart or closer together, because there's the arguments, so gravitational constant may not be a constant. Gravity may decrease with distance away from that. I mean, there's the varying gravity explanations. The electric universe would say the plasma throughout the universe and the Birkeland currents basically hold everything firm. So I mean, there's probably as many theories as to why a static universe stays the way it is as there are people who believe it.
The problem is, it seems your paper is for recessional speed increasing for galaxy. It means that the space must expanding so that the galaxy has space to go when they're.
That's what the mainstream believes, and that's what Gowan his data was trying to show, is that it doesn't follow Hubble's law at greater distances. And if it doesn't follow Hubble's law, then everything based on that redshift equals expansion and expansion of space-time falls apart. So he's saying that, what he was saying is that when they postulate Hubble's law and its linear behavior or the approximation, they're basing it on the redshifts closer to us and not the farther redshifts, because when you look at the data from the farther redshifts, the Hubble law behavior falls apart. So he's not necessarily supporting a expanding universe. He's just saying that it's questionable whether redshifts being equated to recessional speeds should be used as the basis for justifying an expanding universe. Again, if it's tired light phenomenon, it's just distance, and it's got nothing to do with it. The galaxies don't have to be receding. In tired light, this galaxy could be static, and the only reason that you have redshift is because the light interacts on its way into Earth. The farther away it is, the more it interacts, and as it interacts, it loses energy. And if it's a constant light speed, the waveform lengthens and it reddens in that sense. If it's a variable light speed, the speed slows down, the waveform stays the same, the frequency drops, and it's frequency, not wavelength, that determines, quote, color. Though if you believe in a constant speed of light, the two are interchangeable, but it's frequency that is actually the determiner of, quote, color.
But the thing is, if the galaxy recessional speed increase, it gives me a belief that there must be extra room
Sure.
out there for
Yeah.
the universe to go into.
Yeah, and the mainstream just says it creates the the galaxies except create space. You know,
So
I can't explain galactic expansion based on. I don't believe in it. I don't think the universe is ripping itself apart. And a lot of people saying we shouldn't even be able to notice it, because if everything's expanding uniformly, then we are expanding along with the universe, and all our measurements should be staying constant. When they talk about expanding universe, they keep the galaxies the same size, and they just increase the space between the galaxies. So there's an inconsistency there as well. But you know, they kind of ignore that. It was like in the Einstein Wrong video when David interviewed the man at the the Stanford Linear Accelerator. He basically said, yeah, they talk about all this, you know, mass increasing with speed and stuff, but when they actually do the analysis and set up the experiments, they don't use those formulas. And was it Ron Hatch, you know, a couple years ago? They don't use relativity to justify the GPS. They set that up without. I mean, you can use the formulas work and can be used to do all the relativity formulas work, but that doesn't mean Ptolemy's system works as well. It doesn't mean it's the right system, the right explanation.
if you excuse me, I wonder if we can have some compromise, like a space. Universe has infinite space.
I can accept.
Yeah, infinite space. However, what we see as a universe is only a small part of the infinite space. So it is that what we see expanding. It is not the universe. That universe is still far bigger out there.
Sure.
For the visible part to keep expanding.
Well, I mean, even if light speed isn't variable, as time goes by, the light from that was farther away 2 days ago reaches us, and we start seeing theoretically farther and farther out. But it doesn't mean anything's moving. It's just that the light finally got to us.
Okay,
Thank you very much.
We got another question from the internet, and that is, a common argument against the tired light hypothesis is that there should be blurring. Any counter argument to this?
There's many, and I'm not enough of an expert to explain the counter arguments. There's an excellent paper. Actually, Louis Marmé has done an intensive study of all the tired light phenomena, postulated over maybe the last 50 years. And he published a paper maybe 5 years ago, and he reviewed about 100 different tired light theories and the pros and cons of all of them. He's developed his own, and he recently updated that. He's added maybe another 10 or 20. So of those, he probably has found maybe a dozen or more that can explain. Some of them say the blurring is not real. Others say the blurring can be explained consistent with a tired light phenomenon. So while I don't have the expertise to explain that away, there are dissident scientists who say either the blurring doesn't occur if the